For as long as humanity has gazed upward into the infinite darkness, one galaxy has captured our imagination like no other. Sitting 2.5 million light-years away, the Andromeda Galaxy appears as nothing more than a faint, elongated smudge of light in our autumn sky, barely visible to the naked eye. For centuries, astronomers believed they understood this celestial neighbor. We saw it as a calm, majestic spiral of stars, following a predictable path through the cosmos. We thought we had it all figured out, but we were wrong, catastrophically wrong. The story we told ourselves about Andromeda was merely the prologue to a far darker tale. Advanced telescopes like Hubble have spent decades peering into the heart of our nearest galactic sibling, and what they discovered has fundamentally shaken our understanding of how galaxies evolve. This isn't a story of peace and tranquility. This is evidence of cosmic violence on an unimaginable scale. The Andromeda Galaxy isn't the serene neighbor we imagined. It's a predator, a galactic cannibal with a violent and bloody history written in the stars themselves. What we're about to reveal isn't science fiction or speculation. The data is real, the evidence is overwhelming, and the timeline is set. This is the hidden history of the Andromeda Galaxy, and it's far more terrifying than anyone expected. 2.5 million light-years is a distance so incomprehensibly vast that our minds struggle to process it. To put this in perspective, the light from Andromeda that enters your eye tonight began its journey across the void when our earliest human ancestors were just beginning to walk upright on the African plains. This galaxy is home to up to 1 trillion stars, potentially several times more than our own Milky Way contains. It stretches an absolutely breathtaking 220,000 light-years from edge to edge, making it the undisputed heavyweight champion of our local group of galaxies. And lurking at its very core is something truly monstrous. A supermassive black hole containing the mass of 100 to 150 million suns, a gravitational titan far more massive than the black hole sitting at the center of our own galaxy. For over a century, ever since the legendary astronomer Edwin Hubble proved that this mysterious spiral nebula was actually its own island universe, separate from the Milky Way, we've observed Andromeda with a mixture of scientific fascination and cosmic familiarity. We've known for decades that it's hurtling toward us through space. Thanks to the Doppler effect, astronomers can measure the blue shift in its light, revealing that Andromeda is closing the distance between our galaxies at a staggering 110 kilometers every single second. Based on these measurements, scientists have long predicted that in approximately 4.5 billion years, these two galactic giants would collide in a final, cataclysmic embrace that would reshape both galaxies forever. This cosmic collision would trigger an explosive firestorm of new star formation, fling our solar system into a completely new and chaotic orbit, and eventually forge a single massive elliptical galaxy that astronomers have already nicknamed Milkomeda. That was the narrative we accepted. A grand cosmic dance with a predetermined ending billions of years in the future. It was a story that fit neatly into our theoretical models, one that made sense to us, one we felt comfortable teaching in universities around the world. But what if everything we believed was just scratching the surface? What if that serene spiral appearance was nothing more than a mask, concealing a history so violent and brutal that it forces us to completely rethink how massive galaxies grow and evolve? That comfortable certainty began to crumble when the Hubble Space Telescope embarked on its most ambitious survey of Andromeda ever attempted. This wasn't just another pretty picture for a textbook. This was a complete stellar census, an archaeological dig through galactic history that resolved hundreds of millions of individual stars within Andromeda's disk, and in that unprecedented detail, the first disturbing cracks in Andromeda's pristine image began to emerge. Imagine for a moment that you're trying to reconstruct the entire history of an ancient civilization from nothing but a single blurry aerial photograph. You might see the basic street layout, identify a few major buildings, but you'd completely miss the real story. You wouldn't see the old foundations buried beneath modern construction. You wouldn't notice the neighborhoods that burned to the ground and were rebuilt with different architecture. You wouldn't understand the wars, the famines, the golden ages, or the dark periods. To truly understand that city's history, you need to zoom in dramatically. You need to see the individual bricks, read the inscriptions, examine the layers of construction. You need forensic detail. That's exactly what the panchromatic Hubble Andromeda Treasury, known by astronomers as the FAT survey, accomplished for the Andromeda Galaxy. For years, the Hubble telescope painstakingly mapped an enormous section of Andromeda's spiral disk, capturing detailed information about the age, chemical composition, and distribution of its stars. This was galactic archaeology on an unprecedented scale. Astronomers weren't just taking pictures anymore. They were reading the autobiography written in starlight, decoding billions of years of cosmic history from the light emitted by hundreds of millions of individual stars. And the story those stars told wasn't one of peaceful, gradual, steady growth over billions of years. It was a story of dramatic boom and catastrophic bust. While our own Milky Way galaxy has experienced its share of dramatic events and episodic bursts of star formation throughout its long history, the data from Andromeda revealed something far more extreme. The Hubble observations pointed to an absolutely shocking discovery: a massive, galaxy-wide explosion of star formation that erupted across Andromeda's disk roughly 2 to 4 billion years ago. During that relatively brief cosmic period, an absolutely furious wave of stellar creation may have birthed as much as 1/5 of all the stars that Andromeda has ever produced in its entire 10 billion-year existence. Think about that for a moment. 20% of all stars in a trillion-star galaxy, created in just a fraction of its lifetime. Then, just as suddenly and mysteriously as it began, this incredible burst of creation seemed to shut down completely. The star formation didn't just slow down gradually, it crashed. Something catastrophic had happened to Andromeda, something that left permanent scars. This wasn't the signature you'd expect from slow and steady galactic growth, the kind of gentle evolution our models predicted. In the words of one leading researcher studying the Hubble data, what they were seeing looked less like natural growth and more like the aftermath of a massive galactic train wreck. The evidence was overwhelming and pointed to a disturbing conclusion. Andromeda didn't grow primarily by slowly accumulating gas from the intergalactic medium over billions of years, the way we thought galaxies were supposed to grow. Instead, it grew violently by colliding with and completely swallowing another large galaxy whole. This wasn't a minor merger with a small dwarf galaxy, the kind of event we see happening relatively often in the universe. This was a head-on collision between two massive spiral galaxies, an impact that ignited an absolutely unprecedented star-birthing frenzy throughout Andromeda's disk, and then, for reasons that weren't immediately clear from the data, seemed to choke the galaxy's ability to form new stars, leaving it in a state of arrested development that persists to this day. Hubble had essentially uncovered a cosmic crime scene from billions of years in the past. The evidence was everywhere once astronomers knew what to look for. The clues were hidden in the strange, disturbed orbits of stars in the outer disk. They were visible in the unusually puffy, thickened structure of Andromeda's stellar disk, puffed up like a pillow from some ancient impact. They were written in that dramatic burst of star creation followed by an eerie, unsettling quiet that has lasted for billions of years. But every crime scene investigation needs more than just evidence of the crime. You need a suspect. You need a murder weapon. As astronomers carefully scoured the neighborhood around Andromeda, searching for anything unusual, their attention was drawn to one of Andromeda's companion galaxies, a strange, compact little system known to astronomers as Messier 32, or simply M32. This galaxy is a genuine celestial oddball. It's incredibly dense and compact, completely unlike any other dwarf galaxy in our cosmic neighborhood. And as the investigation deepened, astronomers began to realize something profound. M32 might not just be an innocent bystander to ancient violence. It might actually be what remains of the murder weapon itself. To truly understand the leading hypothesis about what happened to Andromeda, you have to completely abandon the idea of galaxies as static, unchanging objects floating peacefully through space. Galaxies are dynamic, living ecosystems locked in an eternal gravitational dance of life and death. Large galaxies like Andromeda and our Milky Way are cosmic cannibals by nature. They grow larger and more massive by gravitationally capturing and devouring their smaller neighbors over billions of years. When astronomers look carefully at the space around Andromeda, we can see ghostly trails and streams of stars, the shredded remnants of past galactic meals, small dwarf galaxies that wandered too close and were torn apart by Andromeda's immense gravity. But the evidence suggests that the M32 event was fundamentally different from these smaller snacks. This wasn't Andromeda casually absorbing a tiny dwarf galaxy. This was Andromeda engaged in an epic battle with a genuine rival, possibly the third largest galaxy in our entire local group. The leading theory, painstakingly pieced together from incredibly complex computer simulations that took years to develop and refine, proposes something remarkable about M32. According to this hypothesis, M32 isn't actually a dwarf galaxy at all, at least not in the traditional sense. Instead, M32 is the dense, stripped-down core of what was once a massive spiral galaxy, a galaxy that might have rivaled even our own Milky Way in size and mass. The simulations tell a story of violence on a cosmic scale that's difficult to even comprehend. The theory suggests that approximately 2 billion years ago, this massive galaxy, which astronomers have nicknamed M32P to distinguish it from the remnant we see today, plunged directly through the heart of Andromeda's disk. Picture two enormous spiral galaxies, each containing hundreds of billions of stars, colliding at speeds of hundreds of kilometers per second. As M32P punched through Andromeda's disk, the immense tidal forces generated by Andromeda's gravity literally ripped the intruder's beautiful spiral arms completely away, scattering billions upon billions of stars into the vast halo surrounding both galaxies. The gas contained within M32P was violently siphoned off and compressed as it slammed into the dense gas already present in Andromeda's disk. This compression triggered that immense starburst that Hubble detected, creating hundreds of millions or even billions of new stars in a cosmically brief period. According to this devastating scenario, all that survived the passage was M32P's incredibly dense core, the central region where stars are packed so tightly that the galaxy's gravity held them together even through this catastrophic encounter. This core survived the collision and was thrown into its current strange, highly eccentric orbit around Andromeda. Today, M32 may be the smoking gun we've been looking for, the definitive remnant of galactic cannibalism on a scale we had never fully appreciated or understood before. This single violent event could simultaneously explain multiple mysteries: the stellar debris scattered through Andromeda's halo, the massive starburst detected in the galaxy's history, the subsequent dramatic shutdown of star formation, and the absolutely weird nature of M32 itself, which has puzzled astronomers for decades. This revolutionary idea fundamentally reframes our entire view of our nearest galactic neighbor. The image of a placid, peaceful spiral galaxy is permanently replaced by the reality of a battle-scarred cosmic conqueror. But this violent history turned out to be just the beginning of Andromeda's mysteries. As astronomers shifted their focus away from Andromeda itself and began carefully studying the dozens of tiny dwarf galaxies swarming around it like satellites around a planet, they discovered something even more profoundly unsettling. A discovery that doesn't just challenge our ideas about how Andromeda formed and evolved, but threatens to unravel our entire standard model of how the universe itself works. Every large galaxy in the universe plays host to a court of smaller satellite galaxies, captured over billions of years by the massive galaxy's gravity. Our own Milky Way has dozens of these satellites, including the famous large and small Magellanic Clouds visible from the southern hemisphere. According to the Lambda Cold Dark Matter model, our standard model of cosmology that has been tested and refined over decades, these satellite galaxies should be captured by the host galaxy's gravity from all different directions throughout cosmic history, resulting in a chaotic swarm of completely random, disorganized orbits. Some satellites should be moving clockwise, as seen from above the galactic disk, others counterclockwise. Some should have highly elliptical orbits, others more circular. They should be distributed roughly spherically around the host galaxy, with no particular pattern or structure. And for the most part, when we look at satellite galaxies around large galaxies throughout the universe, that's exactly what we observe. Random orbits, no obvious structure, exactly as predicted by our theories. But when astronomers meticulously mapped the three-dimensional positions and motions of the dwarf galaxies orbiting around Andromeda, using years of careful observations, they found something that simply should not exist, according to our understanding of physics. They found something genuinely baffling. A huge number of Andromeda's satellite galaxies, far more than chance would allow, aren't swarming randomly at all. Instead, they are all confined to a vast, shockingly thin plane stretching over 1 million light-years across space. And even more bizarre and harder to explain, the vast majority of the galaxies within this plane are all orbiting in the same direction, like cars on a cosmic highway, all traveling the same way. This structure, which astronomers call the Great Plain of Andromeda, represents one of the most significant observational challenges to our standard model of cosmology ever discovered. When scientists run sophisticated simulations based on the Lambda Cold Dark Matter model, feeding in everything we know about dark matter, galaxy formation, and cosmic evolution, the odds of a structure this thin, this large, and this organized forming purely by chance are staggeringly, almost impossibly low. Some detailed statistical studies have calculated the probability at less than 0.3%. It's a statistical anomaly so profound, so far outside the expected range of outcomes, that it strongly suggests either our fundamental understanding of dark matter is incomplete or wrong, or this plane isn't a random coincidence at all, but represents something our current theories simply cannot explain. The team of astronomers who first discovered this structure and verified its reality were genuinely stumped by their own findings. One of the lead astronomers described the Great Plain simply and honestly as weird, openly admitting that its discovery was a total surprise to the entire team, and that years later, they still don't fully understand why Andromeda's satellites appear arranged this way. This is the carefully chosen language of scientists confronting an observational result that appears to break their most fundamental and well-tested theories about how the universe works. This ghostly procession of dwarf galaxies, marching in lockstep through the cosmic void in a structure that shouldn't exist, is far more than just a curiosity. It's a profound mystery that strikes at the heart of cosmology. The existence of this plane suggests these satellite galaxies might share a common origin, that they weren't captured individually over billions of years, as our models predict, but were somehow created together in a single event and have maintained their coherent structure ever since. This possibility has opened the door to some highly controversial and even heretical ideas that challenge the very foundations of modern physics. The standard Lambda Cold Dark Matter model is the absolute bedrock foundation of modern cosmology, supported by decades of observations ranging from the cosmic microwave background radiation to the large-scale structure of galaxy clusters across billions of light-years. This model states that approximately 85% of all matter in the universe is an invisible, mysterious substance called dark matter that doesn't emit, absorb, or reflect light, but whose gravitational influence dictates how galaxies form, how they cluster together, and how they move through space. Without dark matter, according to our current understanding, galaxies would simply fly apart because there wouldn't be enough gravity from visible matter to hold them together. But the Great Plain of Andromeda has given powerful ammunition to proponents of a controversial alternative idea called modified Newtonian dynamics, universally known by its acronym MOND. Back in the 1980s, Israeli physicist Mordechai Milgram proposed a genuinely radical thought that challenged centuries of physics. What if dark matter doesn't actually exist at all? What if the reason galaxies behave strangely isn't because of invisible matter, but because gravity itself behaves differently than we think at the vast scales of galaxies? Mond suggests that at extremely low accelerations, the kind you find in the outer regions of galaxies where stars are far apart, gravity becomes slightly stronger than Newton's laws and Einstein's general relativity predict. This modification could potentially explain why galaxies spin so fast without flying apart, eliminating the need for dark matter entirely. For decades, MOND has existed as an intriguing but fringe theory in physics, gaining a small but dedicated following among physicists frustrated with our inability to directly detect dark matter, despite decades of increasingly sensitive experiments. But MOND has consistently struggled to explain many other cosmic observations that dark matter handles beautifully, particularly the detailed structure of the cosmic microwave background radiation and the way galaxy clusters behave. However, the Great Plain of Andromeda is something that MOND-based theories might actually explain more naturally and elegantly than the standard dark matter model. Some variations of MOND predict that if two large galaxies experienced a close flyby encounter billions of years ago, the extreme tidal gravitational forces during that encounter could rip out long streams of gas from both galaxies. These gas streams would then fragment and collapse over millions of years to form a string of new tidal dwarf galaxies, all naturally sharing a common orbital plane and direction because they were born from the same tidal stream. Suddenly, under this framework, the supposedly impossible plane looks less like a statistical fluke and more like a natural, predictable outcome of galactic dynamics in a MOND universe. This is an absolutely tantalizing possibility for MOND supporters. But despite this apparent success, the wider scientific community has definitely not abandoned the dark matter paradigm. Far from it, in fact. Recent studies of our own Milky Way's rotation curve using extraordinarily precise data from the European Space Agency's Gaia satellite have presented strong evidence that seems to definitively refute the simplest versions of MOND, showing that dark matter provides a much better fit to the observations. Still, the Andromeda satellite plane problem remains a stubborn thorn in the side of cosmology, a puzzle that refuses to go away. This represents a genuine scientific mystery of the highest order, a critical juncture where our best and most successful model of the universe struggles to explain something dramatic happening right on our cosmic doorstep, in a galaxy we can see with our naked eyes. To solve this puzzle once and for all, to serve as the final arbiter in this increasingly heated cosmic debate, astronomers desperately needed a new tool unlike anything that had come before. They needed an eye powerful enough to measure the precise three-dimensional motions of these incredibly faint dwarf galaxies millions of light-years away. They needed an instrument sensitive enough to detect motions almost imperceptibly small. They needed the James Webb Space Telescope. The James Webb Space Telescope is an instrument of absolutely unprecedented power in the history of astronomy. With its massive 6.5-meter primary mirror coated in ultra-thin gold and its exquisite sensitivity to infrared light, wavelengths invisible to human eyes but perfect for penetrating cosmic dust, Webb can observe things that Hubble could never dream of seeing. While Hubble gave us the first tantalizing hints of Andromeda's violent past and revealed the strange satellite plane, Webb has arrived like a master detective with a complete forensic laboratory, perfectly positioned to answer the biggest questions that have been plaguing astronomers for years. One of the most critical and ambitious long-term scientific programs planned for Webb involves tackling the Great Plane of Andromeda mystery head-on with unprecedented precision. A team of astronomers led by Dr. Roland van der Merel of the prestigious Space Telescope Science Institute has developed an ingenious plan to use the combined observational power of both Hubble and Webb over many years to accomplish something that sounds almost impossible: measuring the full three-dimensional motions of these dwarf galaxies with enough precision to finally settle the debate about whether the plane is real or illusory. This measurement is insanely difficult, pushing the absolute limits of what's possible with current technology. These galaxies are sitting millions of light-years away from us, making them incredibly faint targets. Their motion sideways across our line of sight, what astronomers call proper motion, is almost infinitesimally small, measured in tiny fractions of an arcsecond per year. But by comparing hyper-precise images of these galaxies taken by Hubble years or even decades ago with brand-new observations from Webb's Sharper 1, astronomers hope to detect this minuscule motion by measuring how individual stars within these dwarfed galaxies have shifted position against the background of even more distant galaxies. These painstaking measurements, requiring years of observations and extraordinarily careful data analysis, will provide the ultimate test of whether the Great Plane is real. The results will definitively reveal whether this plane is a genuine, physically rotating structure held together by some mechanism we don't understand, which would be an absolute nightmare for standard cosmology, or whether it's merely a chance alignment of galaxies that happens to look impressively organized from our particular viewing angle, but has no real physical significance. The results from this multi-year program could finally provide a definitive verdict on one of cosmology's most stubborn mysteries. But Webb's scientific mission at Andromeda doesn't stop with the satellite plane investigation. Its powerful infrared eyes are also perfectly suited to investigate what astronomers call the cold case of Andromeda's ancient violent merger. While Hubble excels at seeing starlight in optical wavelengths, Webb sees heat. By systematically mapping the distribution of cold dust and molecular gas throughout Andromeda's disk and halo, Webb can trace the thermal evidence and gravitational ripples left over from ancient galactic collisions. These observations can reveal structures and patterns completely invisible to Hubble. Webb can cut through the thick veils of dust that obscure our view of regions near Andromeda's core, revealing faint infrared glows from warm dust that hint at ongoing activity and heating. These observations could show us in unprecedented detail exactly how a massive galaxy collision might trigger cascading waves of star formation rippling through the disk and then mysteriously choke off that formation, leaving the galaxy in its current state. In essence, Webb is methodically putting the entire Andromeda Galaxy on trial. It's gathering the critical evidence needed to solve the two greatest mysteries surrounding our neighbor: the complete truth behind its violent past and the profound meaning of its impossible satellite plane structure. And as new data continues to stream down from Webb's position at the second Lagrange point 1.5 million kilometers from Earth, it's also helping to refine and update the story of our own galaxy's future, giving us an increasingly clear and somewhat chilling preview of our own cosmic destiny. For many decades, the story of the Milky Way's future was straightforward and simple: a direct head-on collision with Andromeda in approximately 4.5 billion years. The two galaxies would merge catastrophically, creating Milkometa. But like absolutely everything else we thought we understood about Andromeda, the truth is turning out to be significantly more complex and nuanced. Recent, far more precise measurements of Andromeda's motion from both Hubble and the European Space Agency's Gaia satellite which has measured the positions and velocities of over 1 billion stars with unprecedented accuracy, have allowed astronomers to run the most detailed and sophisticated computer simulations of the future collision ever attempted. These simulations can now account for the gravitational influences of not just the Milky Way and Andromeda, but also the effects of other nearby galaxies like Triangulum and the complex distribution of dark matter throughout our local group. The results of these new simulations delivered a fascinating and unexpected twist to our cosmic fortune. A direct, catastrophic head-on crash between the galactic cores is no longer considered a certainty. Instead, the most recent research suggests our future may involve a much more complex and chaotic gravitational dance. The gravitational pull exerted by other nearby galaxies adds new variables to the calculation, and it's now considered quite possible that our two galaxies could experience a series of glancing blows or dramatic near misses over billions of years, with the galaxies swinging past each other multiple times, exchanging momentum and angular momentum before they finally lose enough energy to merge completely. Our galaxy's death sentence might have been commuted from a single catastrophic impact to a long, drawn-out, messy cosmic waltz that plays out over many billions of years. But this is where the story takes its most mind-bending and profound turn. While the final merger of the galactic cores, when the two supermassive black holes finally unite, might be more complicated and distant than earlier predictions suggested, in another very real and physical sense, that's not just poetic language, the collision between the Milky Way and Andromeda has already begun, right now, today. Astronomers studying the vast, diffuse halos of extremely hot gas that surround both the Milky Way and Andromeda, gas so tenuous and spread out that it's effectively invisible to normal telescopes, but detectable through specialized observations, have made an astonishing discovery that completely reframes our understanding of when the merger begins. These enormous, nearly invisible atmospheres of million-degree gas extend out